Yeah. So we'll move to the last speaker of this session. We'll have Dr. Suraj Ravindran. He's a postdoctoral fellow at the Department of Aeronautics at Caltech, and he's going to talk to us on strength measurement of materials at extreme pressures and strain rates. So over to you, Dr. Ravindran.
Thank you for the introduction. My name is Suraj Ravindran. I am a postdoctoral scholar at Caltech. So I'd like to thank first for inviting me for the talk. So, from Caltech, we would like to thank Dr. Simha for all his contribution, and we wish him a wonderful retirement life coming ahead. Today, I'm going to talk about strength of materials at high pressures and strain rates. Strain rates, in simple words, it is the deformation, the change in deformation with respect to time. So if you deform a sample at a velocity of v, and if you know the initial length, then you can calculate the strain rate by using simple equation as you see here. The strain rate can be significantly high in events such as high rate events such as car crash, where the strain rate can be in the order of 10⁻�3. So whereas in a bird impact event that happens on an aeroplane, the strain rate could be even higher in the order of 10⁻⁴. So the material strength is significantly affected by rates. Therefore, the characterization is extremely important in order to develop the material of superior performance. So at this strain rate, ranging from 10⁻² to 10⁻⁴, we could use a split Hopkinson pressure bar to characterize the material. Whereas when you go to higher impact velocities, such as the one you see here, it's a ballistic impact. That is actually what they do is they launch a projectile at a velocity of 2.3 km/s, and when it impacts an armored vehicle, the strain rate can be extremely high. So therefore, characterizing materials at this ultra high strain rate is very important. In this kind of impact scenario, not just strain rate is important, also it generates a significantly high pressures upon impact. So a typical experiment setup that is used to characterize materials at this kind of high strain rates and pressures are simple plate impact experiments. And the pressures we can achieve in these experiments are as high as 500 gigapascal, and rates we can go up to 10⁸ per second, depending on the impact velocity. A simple plate impact experiment is shown here. When a plate impacts another plate, it's a thin plate, it's a circular plate. When it impacts another one, it generates a longitudinal wave, and at the same time, there will be lateral release coming from the edge of the sample towards the center. As you see here, the impact velocity would be very, very high. Therefore, the material in the longitudinal direction deform very fast. So the material around the center of the sample cannot laterally deform. Therefore, if you look at the center of the sample, it will be under uniaxial strain condition. Since the material around the center of the sample cannot laterally deform, therefore, the stress state in the material would be close to a hydrostatic stress state. The velocity of the longitudinal wave that is generated in the material during the normal impact is usually higher than the sound speed in the material. Therefore, these are also called shock compression experiments in solids. So what we measure in this experiment is nothing but free surface velocity using a photon Doppler velocimeter. As you see here, this is a typical free surface velocity profile of an elastic plastic material, and this part represents the elastic behavior of the material. As you see here, this deflection is corresponding to the yield strength of the material. So this is called a Hugonian elastic limit. This is nothing but the yield strength of the material under uniaxial strain condition. This final state is called a Hugonian state. So from this velocity measurement, we can calculate the normal stress using simple equation as you see here. So your ρ0 is the initial density, us is the velocity of the shock which is propagating along the longitudinal direction, up is the particle velocity. The up and free surface velocity that we measure on the back side is related by ufs divided by 2. So the next thing with the parameter we need to know is US. And it's interestingly, for most of the metals, US and UPS are related through a linear relationship. Therefore, we could do experiments to get the C0 value and S to calculate the shock velocity later with from the particle velocity. So we can calculate the normal stress from the simple free surface velocity measurement we do on the backside of the sample. However, this experiment setup we cannot directly use to calculate the strength of materials at high strain rates and pressures. Therefore, in early 80s, there is a setup that is developed in Brown University, where an inclined plate impacts a sandwich assembly, as you see here. So here, the sample to be tested for strength is sandwiched between two anvils. One is a front anvil and then rear anvil. The strength of these front and rear anvil are relatively high compared to the sample to be tested, which is sandwiched between these plates. So how this experiment works, so this is an XT diagram. So when this inclined plate hit the front plate, as you see here, it generates both longitudinal and shear wave. Since the longitudinal wave is faster than shear wave, it reaches the sample first and compresses to the required pressure that is designed this experiment is for. Then the shear wave comes in and shear the sample, and that information could be used to calculate the strength in the material. So as I mentioned, what we typically measure is velocity on the backside of the sample, and they are called free surface velocity measurements. In this experiment, in the inclined plate impact experiment, we measure not only normal velocity, but transverse velocity as well using photon Doppler velocimeter. So in order to do that, we have a diffraction grating on the sample, on the backside of the sample. So when we shine light onto it, it generates a zeroth order diffraction and a first order diffraction. The zeroth order diffraction would be used to measure normal velocity, and the transverse velocity measurement is done using the first order diffraction light that is coming out of it. In this experiment, if this front anvil and rear anvil stays elastic, then we can calculate the normal stress using this equation, where rho is the density of the sample and C1 is the longitudinal sound velocity, elastic sound velocity, because these plates are below the Hugoni elastic limit of that material. Therefore, we can use a elastic longitudinal sound velocity, and UFS is the free surface velocity. From this, we can calculate the normal stress. Whereas the shear stress in the sample, we can calculate it by using similar equation, but we have to use the shear wave velocity and free surface transverse velocity that is measured on the backside of the sample. So if you wanted to actually go to higher pressures, these plates do not remain elastic over the Hugoni elastic limit. So most of the materials have Hugoni elastic limit is in the order of 15 it's close to 15 gigapascal or smaller, except diamond has 60 gigapascal, but we cannot use diamond for this kind of application. Therefore, we need to account a plasticity of these anvils for our measurements if you want to go to higher pressures in close to 40 or 50 GPa. One of the main advantage of this experiment, as one of the previous speaker was saying, there is in plate impact experiment, there is a coupled effect from pressure, temperature, and strain rate. So in this experiment, we can actually decouple the effect from pressure and strain rate, but by properly designing this experiment. So as I said before, we need to include the plasticity of the anvil if you want to go to high pressures. So we developed a hybrid technique to estimate the strength using simulations. So as you see here, so what we do in this procedure, first we characterize this anvil material at similar pressures. So we do a symmetric PSP experiment on anvils, then calibrate an inelastic model for this material. Then we perform the sandwich experiment, and since we know the calibrated material behavior of this material, the only unknown is the strength behavior of this sandwich material. So this is the experiment setup we have. It's a powder gun. We launch projectiles that the velocity can be varied from 0.2 to 2 km per second. When it impacts the target assembly, it generates both longitudinal and shear waves, as I mentioned before. So we measure normal velocity using the normal probe and the transverse velocity using the transverse two probes that is placed at an angle, as you see in this figure. So in our procedure, the first thing we need to do is to calibrate a material model for the annual material. So for that, in this experiment, first we have used D2 tool steel anvil. So we have done experiment at 10 GPa and 15 GPa to calibrate the material model for the annual material. So this is the normal velocity that we measured at 645 meter per second, which correspond to 15 GPa, and the inclination angle that we chose was 18 degree. At 541 meter per second, which correspond to 10 gigapascal, this is the normal velocity profile we obtained. So these solid curves are the experimental results, and this is the transverse velocity profile that we obtained at impact velocity of 541 and 645 meter per second. The peak transverse velocity we observed was 40 meter per second at 541 meter per second. At 645 meter per second, it's around 50 meter per second. In order to calibrate a material model, we used a simple power law model for strain hardening, as you see here, and a strain rate hardening model was used as a Cooper-Simons. These parameters, which is A is equal to 850 megapascal and B is equal to 150 megapascal, N is equal to 0.24, which gives a very good match between normal and transverse velocity profile. So to be noted here, in this experiment, it's a more constraining data set to calibrate a material model, because you need to simultaneously match not just normal profile, you need to match both normal and transverse velocity profile in order to have a good calibrated parameter. So what we observed was, we can change these parameters and we can still match your normal velocity profile relatively well, but matching transverse velocity profile was very difficult. Therefore, these parameters are actually unique for D2 tool steel that we used in the first study. Now we have a material model. Now we are going to do a sandwich experiment at similar pressures and strain rates. In the sandwich experiment, so as I mentioned before, the sample is sandwiched between the front anvil and rear anvil. The sample thickness in this experiment is around 170 micrometer. So when this hit at the front anvil, it generates both longitudinal and shear wave, which is used to measure material strength at high pressures and strain rate. The impact velocity in this experiment was 545 meter per second, and skew angle was 18 degree. So what we targeted was, the pressure targeted was 10 gigapascal, and the strain rate we targeted was 10⁵ per second. The sample material in this study, we used OFC copper, which is a very well studied material, so that we can actually compare the data what we get from this experiment with the previously reported value of yield strength. So this is the normal velocity profile we got for 10 GPa experiment, and this is the transverse velocity profile. So as you see here, even though our imposed velocity, transverse velocity is 168 meter per second, the transverse velocity we measured on the backside is close to 15 meter per second. So this is the direct reflection of your strength of the copper that is sandwiched between these front and rear anvil. So now we have to get the shear strength of the material through simulation. So in order to do that, we know our anvil material calibrated parameters, and we have used a similar model for copper with strain hardening power law. A is equal to 250 megapascal, B is equal to 100 megapascal, and N is equal to 0.24. The strain rate hardening again modeled using Cooper-Simons, as you see here, which matched the normal and transverse velocity profile relatively well. The equation of state, which is the US-UP relationship that what we used here, is shown as C0 is equal to 3933, and S equal to 1.52. So this value we obtained from the previous shock data on OFC copper. So now we have a very good match on transverse and normal velocity profile. We can extract the shear strain rate, which was the average shearing rate we obtained was around 2.7 e raised to 5. Whereas the shear stress versus shear strain curve is shown here, which shows the yield shear strength at 10 gigapascal at a strain rate of 10 raised to 5 is close to 250 megapascal. So in order to compare with the previously reported data with elastic anvils, so there is a study that is done in 1998 in Brown University. What they have shown was the toe peak at a strain of 26% is close to 340 megapascal. The pressure they achieved was 7.8. So what we obtained from simulation in this study is also very close to what the reported values. Therefore, now we have a robust method to extract the strength of materials at these kind of pressures and strain rate. If you want to go to higher pressures and strain rate, you need to have a stronger anvil. The steel cannot sustain a stronger impact, which correspond to higher pressures. Therefore, we have used a tungsten carbide anvils for the coming experiments that I am going to explain. So this is an experiment that is done on tungsten carbide by our colleagues, Christian Kuttenbiel and Sevilla Minger. So this experiment is done at two pressures. One is at 15 GPa and another one is at 28 GPa. So they have calibrated a material model for these two experiments, which match the normal and transverse velocity profile relatively well. So the initial part was difficult to match because the friction property between these interfaces remain unknown. Therefore, we did not model the interface between the front anvil and the flyer. But the peak transverse velocity profile is relatively matching very good. Now we have an anvil material model for tungsten carbide. So its HEL is close to 6 gigapascal. In comparison to D2 tool steel anvil, it is close to 3 times the HEL of D2 tool steel anvil. So now we have done experiment at different pressures and strain rates. This is a sandwich configuration as I showed before. So we have done three experiments. One is at 210 meter per second and one is at 624 meter per second and finally at 924 meter per second. The pressures we targeted were 10 gigapascal and 28 gigapascal and finally 45 gigapascal. So we changed the skew angle in order to keep strain rate to be constant. So which I will give you the strength of material at a fixed strain rate, but changing to a different pressures. So the sample thickness was same as before, but this flyer and front plate and back plate dimensions are changed according to the experimental design. So this is the three experiment result that is obtained for copper at 3 different pressures. This is at 10 gigapascal, and this is at 28 gigapascal, and this is at 45 gigapascal. This is the highest pressure that is achieved in PSPI successfully. So this is the first experiment that achieved this pressure in PSPI. So this transverse velocity profile is shown here. This is at 10 GPa, and this is at 28 GPa, and this is at 45 GPa. A higher transverse velocity measurement directly indicates the pressure changes the shear strength of the materials at these pressures. So as I said, the strain rate is constant for all the experiments. Therefore, this strength enhancement is solely coming from pressure. So we have used a similar material model to see if we can really predict the behavior at different pressures. So this is a 10 GPa experiment, and we can match our we can match the transverse velocity profile relatively well. As you see here, this pink broken lines are for 10 gigapascal. But as you go to higher pressures, since this material doesn't have any pressure dependence to it, so we cannot predict what is going on in 28 gigapascal experiment. Therefore, we cannot use this simple model to predict the behavior of this material at high pressures. So in order to do that, we have used a Steinberg model, which is a pressure dependent model, as you see here. So in this model, one of the main assumption they make is the strain rate cannot increase the shear strength forever. So they have a cutoff strain rate as 10⁵. Over that, they assume the strength enhancement is solely coming from pressure. So this equation shows the flow strength of material as a function of pressure and shear modulus changes. So this part is for thermal softening, and this is for the pressure dependence. And also in their model, they have G to B, which is the shear modulus, changes as a function of pressure. The typical dependence they showed for pressure was linear, and that will be modeled in the experiments. So Gp prime, which is the dg by dp, which is the change in shear modulus with respect to pressure, and Yp prime, which is the change in yield strength with respect to pressure, and that is normalized with the initial yield strength, and this is a constant. So what dependence you get is a kind of a linear dependence to pressure on strength. The initial part is used to capture the strain hardening, and as you see here, this epsilon I have a specific significance in the model, and which actually gives the initial pre-strain in the sample. So if your sample has a different type of core work that is done before the experiment, then this epsilon I has to be given to the equation. This epsilon is the plastic strain, and beta, n, and y0 as the initial constants which we have to calibrate. The final parameters that we obtain for this material for copper is shown here. So these parameters are actually previously reported, but we had to change the pressure dependence in order to match our normal and transverse velocity profile. So I will go to our experiment and simulation. This is the 10 GPa experiment that is done, and which gives a very close match in the normal velocity profile. This is at 28 GPa, and this is at 45 GPa. As you see here, with a single set of constants, we were able to match the peak of the transverse velocity profile relatively well. So as I mentioned before, this initial part cannot be matched because we don't have an understanding of friction law between the interface between the two flyers, which will be a part of future work that we are planning to do. But the peak is matched relatively well. Therefore, this can be called acceptable for strength measurement. So as you see here, this is the shear stress versus time graph, where this is at 10 GPa at a strain rate of 10⁵, and this is at 28 GPa, and this curve shows at 45 GPa. At a given time, if you see, the 10 GPa gives a strength of around 250 megapascal, and 28 GPa is around 430 megapascal, whereas at 45 GPa is at 600 megapascal, which shows a strong dependence on pressure. The yield strength, the shear strength is a strong dependence of pressure. So interestingly, if you remember the D2 tool steel anvil study, we have done a 10 GPa experiment in there as well, which actually gave a shear strength close to 250 megapascal at the initial at the yielding. So which actually matches with this tungsten carbide the study with tungsten carbide as well. Therefore, which actually shows the repeatability and robustness of the method we developed. To compare it with the previous study that is done on copper, so this is the shear strength versus strain rate. As you see here, it has a logarithmic dependence. So these experiments are without pressure, and this experiment had a pressure ranging from 2 to 5 GPa. And interestingly, if you see at a fixed strain rate, if you change the pressure, the strength increases drastically. Therefore, in order to have a complete characterization of this material, you need not just strain rate, but also pressure to completely characterize these materials at high pressures and strain rate. Finally, I will summarize with the following points. We have measured the strength of copper pressure ranging from 10 to 45 gigapascal using a very newly developed hybrid methodology. And we have achieved the highest pressure that is achieved in PSPI so far. And also, interestingly, the shear strength increased by a factor of 2.5 when the pressure increased by a factor of 4.5. So the pressure dependent model that is developed by Steinberg were able to capture the behavior relatively well. As a future study, what we are planning to do is experiments at different rates, but fix the pressure. So we can do that by changing the impact velocity, by keeping the normal velocity same, but changing the transverse velocity by changing the angle of impact. And understand the microscale mechanism that causes the pressure dependent strength, probably through molecular dynamic simulation. So interestingly, this flow strength model doesn't have a rate dependence, as I mentioned before. Therefore, this model cannot be used from lower strain rates to high rate regime. So if you wanted to capture the behavior in this lower rate regime, which is strain rate controlled, you need to have a strain rate term in the flow strength behavior. So we are currently in a process of developing the material model to describe this behavior from a lower rate to a high rate that is seen in the study. At the same time, the effect of pressure dependence on the shear strength. Thank you. Any question?
Yeah, so thank you, Dr. Ravindran, for a interesting talk. Thank you, Dr. Ravindran, for a very nice talk. So Mr. Ishwar, Dr. Ishwar, you have a question?
Yeah, thank you, Professor John.
Yeah.
Suraj, it's a very interesting talk. So far what we learned from our basic understanding of dislocation mechanics is that hydrostatic pressure doesn't have any role in the deformation, right? But what you've shown that with the pressure, the strength goes up as well, right? So what is the fundamental mechanism for this phenomenon?
That's an interesting question. Hello, can you hear me? Hello?
Yes, go ahead.
Yeah. So at these kind of high pressures, what happens is that dislocation drag plays a significant role. So if you see FCC material, so it has to actually go through obstacles. So Pearl stress in copper is relatively small. So lattice friction is not a big thing, but the interesting thing is going to be the force of dislocations present in copper. So at a high pressures, the dislocations move faster. So there will be a drag playing a significant role in the pressure dependence. So that's what an explanation I would have for pressure dependence in copper at this point.
Thank you, Suraj.
Okay. I don't see any other questions in the.
Joke that there's a question in the Q&A box. Parag.
No. Okay, but that is Parag Tande. Yeah. Is the temperature right? Yeah, you can Parag Tande. You can directly ask the question.
Yeah, you just have to unmute yourself.
Yeah.
A very nice talk, Suraj. I just wanted to ask regarding the temperature rise during the high pressure impact, plate impact experiments. Have you measured the temperature rise, and or do you anticipate it to be significant enough?
That's a very good question, actually. 45 GPa, we believe, so we have calculated using an isoentropic. First, to be noted, this is not a sudden jump from one state to another, because it's the wave reverberate in the sample. Therefore, the temperature rise is not as high as shock compression experiments. There is no sudden jump in the experiment we conducted. The temperature increase would be, so we have calculated to have a ballpark number. So it's around 200 Kelvin as the temperature rise. So, and also at the same time, the melting point of copper also increases at these pressures. Therefore, a temperature softening may not significantly affecting the behavior we observed in the material.
Okay, I have just one more question, if Professor Joe can allow me.
Yeah, sure. Yeah, go ahead. Yeah.
The question is, in your simulations that you have done, the simulations of plate impact that you have done in the hybrid approach, how did you account for the equation of state?
Oh, so we have a linear equation of state that is given, right? So we have a linear equation of state we used in the material model, which model the hydrostatic behavior of the material. Does that answer your question?
Okay, fine. Thank you.
Okay, there is one more question from Dr. Rajesh Kumar Meena. So can you, Dr. Meena, can you just ask your question? You have to unmute yourself and then ask the question. Dr. Meena?
Hello, sir. I am a student. I am not doctor. So my question is that, so when you are doing this Johnson model, so can we do this same model with Johnson-Hook model?
Oh, this is actually nothing but a Johnson-Cook model with a slightly different rate dependence. So it has a copper cement rate dependence. What we saw was Johnson-Cook model was not able to capture the transverse velocity profile we saw in our experiments. It's a wonderful question. You brought it up. So in higher rate dependence, what we saw was Johnson-Cook was not really giving good results for the transverse velocity profile we saw. So that's why we had to use the Copper-Simons model to capture the behavior.
Okay, sir. Thank you. Would you like to share this paper so we can go through these also?
Oh, sure.
Okay, sir. Thank you.
Okay, actually, so I don't see any other questions. Any other questions? Yeah. Any other questions, or I don't see any other questions? Yeah.
Somehow the voice is breaking.
Voice is breaking.
Professor Simha, your voice is breaking. Can you say that again?
I'm wondering whether you had a chance to look at the grain structure of the impact test.
I could not hear.
I think he was asking about whether you've looked at the grain structure after the impact test.
So this experiment, we were not able to recover the sample because this tungsten carbide is highly brittle. So as soon as the impact is done, it's crushed into pieces. So there's no way we could recover this sample from the experiments. So we haven't done that. But previously, I think people have done looking at the microstructure of materials at this kind of pressure.
Increase in shear strength due to nanofragmentation.
I could not. So the voice is breaking somehow. I could not hear.
Yeah, Simha, the voice is breaking up. Simha, are you there?
Professor, perhaps he can type it in later. We can
later. Yeah, I think we can move on. Yeah. So I think we are at the end of this particular session. So I would like to thank all the speakers, Dr. Surendra, Dr. Lavingar, Dr. Kannan, and Dr. Ravindran for very interesting talks.